Decomposition to BCNF. Decompose using A to CF, that is R1ACF, and another set relation 2 is R2 of ABDE. Then decompose R2, we have CD BE, R2 using BE, R21 is BE, and R22 is ABD. B is key in R21. Then decompose R22 using CD. CD, we have this as R221 as CD and R222 as ABC. C is key in R221. ABC is key in R222. So final BCNF relations are R1ACF, R21 BE, and R221 is CD, R222 is ABC. So all are in BCNF. Now define Boy's code normal form. How does it differ from 3NF? Why is it considered stronger than 3NF? Boy's code normal form BCNF. A relation R is in BCNF if for every non-trivial functional dependency X depends on Y that holds in R, X is a super key. Difference between 3NF and BCNF. Here condition is for third normal form, for every functional dependency X to A, either X should be a super key or A should be a prime attribute. In BCNF, for every non-trivial functional dependency, X must be a super key. This allows some dependencies where determinant is not a super key. If RHS is a prime attribute, that will be allowed. No such dependencies, determinant must be a super key. Strength, weaker, stronger. Lossless decomposition, always possible, always possible. Dependency preservation, always possible, may not be possible in BCNF. For example, we have RABC, functional dependencies A to B and B to C. Candidate key is A. Functional dependency B to C. B is not a super key, but C is a prime attribute, part of the candidate key. So R is in 3NF. Check for BCNF. For B depending on C, B is not a super key, hence 3NF allows this dependency, but BCNF doesn't allow. Why BCNF is stronger than 3NF? BCNF has a stricter condition, determinant must be a super key for every non-trivial functional dependency. Every BCNF relation is in 3NF, but not every 3NF relation is in BCNF. BCNF eliminates more redundancy and anomalies caused by dependencies whose determinant is not a super key. So difference between prime and non-prime attributes with example. Prime attribute. An attribute that is a member of any candidate key is called the prime attribute. Non-prime attribute, an attribute that is not a member of any candidate key is called a non-prime attribute. Example, consider relation R student ID, course ID, instructor ID, room number, time slot. Functional dependencies, course ID to instructor ID to room number, time slot, student ID and course ID to instructor ID to room number and time slot, room number to time slot. So prime and non-prime attributes are here. The candidate keys are student ID and course ID. Prime attributes student ID, course ID. Non-prime attributes instructor ID, room number, time slot. Summary for this: prime attributes part of some candidate key, not part of any candidate key. Prime attributes are important in 3NF condition. Find candidates keys. How to find this? From 1, to get the instructor ID we need a student ID and course ID. From 2, instructor ID gives room number and time slot. From 3, we have room number gives time slot already obtained. Student ID and course ID closure plus gives you the student ID, course ID, instructor ID, room number, time slot, that is equals to all attributes. Thus, student ID, course ID is a candidate key. No other smaller set of attributes determines all attributes. All attributes of relation are either prime or non-prime. State the informal guidelines of relational schema design. Illustrate how violations of these guidelines may be harmful. Informal guidelines of good relational schema design. Clear semantics. Each relation should represent one entity or relationship, and its meaning should be clear. Minimize redundancy. Store each fact in one place only. Minimize null values. Avoid attributes that are not applicable for many tuples. Avoid spurious tuples. Decomposition should be done in the way that prevent generating the spurious tuples or joined. Lossless join decomposition. Decomposition should allow us to retrieve the original loss of information. Lossless join. Dependency preservation. All functional dependencies should be preserved after decomposition as well. Simple and small relations should be small and simple to understand and maintain. Insulate from insertion, deletion, update anomalies. How violations are harmful. Violation of redundancy. Harmful effect is waste of storage and update anomalies. Insertion, deletion, and modification. Many nulls, wastage of storage, misleading information, difficult constraints, spurious tuples, incorrect information retrieved after join, wrong results. Lossless join. Information loss when decomposed cannot reconstruct original relation accurately. Dependency preservation. Some constraints cannot be enforced easily. Applications become complex. Complex relations, hard to understand and maintain, higher chance of errors. Insertion anomaly. Cannot insert a fact without having other unlisted, useful, unrelated facts. Deletion anomaly. Deleting a tuple leads to loss of other useful information. Update modification anomaly. Some fact appears in many tuples. Updating one but not all leads to inconsistency. Here is an example for that. We have violation of redundancy here. Student ID, student name, department phone. Department phone depends on department name, not on the whole key student ID. If department phone changes, update must be done in all tuples of that department. If not, inconsistency occurs, that is update anomaly. For an instance, we have student ID, department phone 11111 and all. If phone of CSC changes to 99999, we must update in all CSC tuples, otherwise inconsistency occurs.